So an outcome is like rolling a 4 on a dice. It's just some outcome that we can have in a experiment, okay? Now, an event is a result or a group of outcomes for an experiment, okay? So we could think of that as like rolling an even number on a dice. How many options do I have to roll an even number? 2, 4, and what? Because you can do 2, 4, or 6. So there's multiple options, right? You can also consider an event to be like rolling a 4 on a dice. That's fine. But like usually it's something a little bit more to it than that. Okay, then the sample space is the set of all possible outcomes of an experiment. So yesterday we actually created a sample space. So if we look back at this page here, okay, when we did this for all the possible combinations of rolling 2 dice, we created a sample space. So we can write sample space for a lot of different types of experiments. But like reasonably, would I want to write a sample space for rolling 1,000 dice? No, because you'd have to go 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1. It'd just take forever, right? Okay, we would not want to do that. Now, what would the sample space be for flipping a coin, though? Not 1 and 2. What do we usually call it? Heads and tails, right? What about the sample space for rolling 1 die? What are all of our possible outcomes for rolling 1 die? 1, 2, 3, 4, 5, 6. Okay? Yes. How many different things are in the sample space for a standard deck of cards? 52. Right? We have 2 through 10, 4 different times, and we have all of our Jack, King, Queen, Ace for 4 different suits. Okay? So the sample space depends on what type of sample we're looking at. Okay? But we can find it for any of those. Okay? Now, a probability measures how likely an event is to become. Okay? So, to find a probability, okay, over here at the side, we're going to write how to do this. So, we're going to do the probability of an event is equal to, we're going to create a fraction. Okay? The numerator is going to be the number of favorable outcomes. So the top is whatever we want to happen. And the bottom is going to be out of the total number of outcomes. So if I use the example for the probability of rolling, the probability of rolling a 2 with a dice. How many different ways can I roll a 2 on a dice? 1. Out of how many ways can a dice land? 6. So the probability of rolling 2 on a dice is 1 out of 6. Okay? What if we did the probability of drawing a king? How many kings are in a deck of cards? 4. Out of how many total cards? 52. Now, that is something we can simplify. What can go into both 4 and 52? 4. What is 4 divided by 4? What is 52 divided by 4? 13. So your chances of drawing a king is 1/13. Okay? So that's the different ways we can consider a probability. So we take the number of favorable outcomes, the number of the outcomes we want, out of the total possible that we could have. Okay, then we have two different kinds of probabilities that we're going to look at. Okay, so we have a theoretical probability, which that is found by dividing the number of favorable outcomes by the total number of possible outcomes. It's what we expect to happen. And we use the sample space for that, right? We typically use sample space. So like the probability of rolling an even number on a dice. How many even numbers are on this dice? Out of how many? What is 3/6 the same as?
1/2.
So the probability of us rolling an even number is 1/2. Okay? But we have something called an experimental probability. Which is found by the number of times an event actually occurs in an experiment by the number of total trials. Okay? So this, let's see. I'm going to roll this 5 times and we're going to see how many times I get an even number. Okay, ready? 1, so that's odd. 1 again, that's also odd. 4, I got one even number. 4. 6. Okay, so 3 out of 5 times. So I rolled even. Okay, is 3 out of 5 the exact same as 1/2? No. Okay, because what actually happens in an experiment won't always align with a theoretical thing. And we saw that happen yesterday. So I'm going to flip back to our page from yesterday real quick. So yesterday we all played the game. We had the 2 dice, we rolled them, we see which player won, right? And we calculated our class's data. This is us doing an experimental probability. Then we said, okay, let's see what's actually going to happen, like what our actual chances of stuff happening is. And so we looked at the sample space. And we calculated these. Those are our theoretical probabilities. Are those the exact same? No, but are they pretty close? There's something called the law of large numbers, which basically says like the more something happens, the more likely something is to occur. So the more we do an experiment, right, the closer and closer we're going to get to those numbers. So second period yesterday did the experiment a couple more times than y'all did. And let's look at their data. So if I compare their theoretical probabilities to the actuals, look how close those are. How far off are both of those? Just 1%, right? They're super close. So our goal is for our experimental to match the theoretical, but Can we control how many times a dice rolls even? No. Okay? But we can calculate the theoretical probability of it happening by using the sample space. Okay? Because we know what should happen, and so we can do that. So theoretical is what should happen. Experimental is what actually happens in an experiment's data set. Okay? So that's the difference in the two. If most of the time we'll be looking at theoretical, and if we're not, I will give you the experimental data. Or we will do the experiment, then use the experimental data. Okay? But you're still taking the total number of desired outcomes, what you want to happen, out of the total outcomes. It's the same way to calculate both. It's just they mean slightly different things, because one of them is you're taking an experiment with a small group of people, whereas the theoretical is taking what should happen in a perfect setting, in a perfect world with no weird things happening. That's what theoretical is. Whereas experimental is what's going to happen in the real world. Okay? So now, right here on this next blank, okay, we're going to write out how we write out probability problems. So if you are trying to find the probability of event A, how you would do that is you would do the probability of A. So that means the probability of event A. That could be the probability of rolling a 6, the probability of an even number, whatever, but that is the notation we use to write out how to find the probability. So if event A is rolling a 3, then the probability of A is equal to, how many different ways can I roll a 3 on this dice? Out of 6. That's what it means. That's all it's meaning. Now, we're going to look at some symbols. So, we've actually used both of these symbols earlier in the year before, and they still mean the same thing. We're just using them slightly in different context. Okay, so the union symbol, which is just a capital U, means or. And we can use that in a probability. So if we have the probability of A union B, that just means the probability of A or the probability of B. Okay, we can also have intersection. The symbol for intersection is an upside down U or a lowercase n. And so the probability of A intersecting B is just the probability of A and B. And the way I kind of remember that is U union, right? And you're joining together in holy matrimony. So it can, union, you're becoming one. And then intersection, in, which is where we get that symbol from, we're looking for the specific place that two things intersect. Like the specific intersection of airport and Schillinger. How many times does airport and Schillinger intersect?
I don't know.
One, right? Because one goes this way, one goes this way. Okay? So we're looking for a specific intersection. Whereas a union, if I say the Williams, because me and my husband got married, right? When I say, well, we need to talk to one of the Williams, could that mean me? Or it could mean my husband, right? It could be either of us. Now, I want us to have a conversation about this dice. So if I wanted to take this dice, we're good. We're still good. There it goes. Okay. If I wanted to take this dice and I want to roll it and roll both a 2 and a 5, dice be both a 2 and a 5 at the same time?
Oh no, hold on, I'm thinking of two
Right?
dice. Hold on.
Because only one dice can only have one side up at the same time, right? I can only roll one number at a time. Okay? So if we have something that cannot happen at the same time, those two events are considered to be mutually exclusive. Means they cannot happen at the same time. Okay? That's what that means. I can only roll one number at the same time. Okay? So an example of that is rolling a 1 and a 3 at the same time. Okay, then we're going to look at, go ahead and flip to the next thing. Okay. So, these two rules apply specifically when the events are mutually exclusive. Okay? So, we have something called the addition rule of probability. So if we have two mutually exclusive events, the addition rule is used to find the probability of event A or event B. And what that rule is the probability of A union B is equal to the probability of event A plus the probability of event B. So if we are looking at rolling the probability of rolling a 6 or a 2. We can't roll a 7. Okay? Is equal to, okay, the probability of rolling a 6 plus the probability of rolling a 2. What is the probability of us rolling a 6 on a dice? 1 out of 6. What's the probability of us rolling a 2? Also 1 out of 6. What is 1/6 plus 1/6? And we can simplify that to what? 1/3 or 33%. Okay? So by saying a 2 or a 6, it pretty much doubles our probability, right? Of doing either of them. Now, in a mutually exclusive condition, okay, the complement rule helps us to find the probability that an event does not occur. So we can do this by saying, to find the probability that it is not event A, we can say 1 minus the probability of A. Or we can do the opposite. The probability of A is equal to 1 minus the probability of not A. So if I ask you the question, the meteorologist said that today has a 20% chance of rain. So what is the chance of it not raining? 80. You did 100% minus 20%, right? That's the same thing that's happening there, except we're doing it without the percents. We're doing it as the decimal equivalent. So if I said, let's see. The probability of not rolling a 2. We're going to do 1 minus the probability of rolling a 2. So 1 minus, what's the probability of rolling a 2? 1/6. What is 1 minus 1/6? 1 is the same thing as saying 6 over 6, which, what is 6 over 6 minus 1 over 6? 5/6. Yeah. 5 out of 6 chances of us not rolling a 2. Because how many of these sides are not 2? 5. Okay? Now, all probabilities are less than or equal to 1 and greater than 0. Okay, so probabilities of any event has to be greater than 0 or greater than or equal to 0 or greater than or equal to 1. Because can I roll a 7 on this dice? No. So what's the probability of rolling a 7? 0. Okay, we can have a probability of 0. What if I said, what's the probability of me rolling a number 1 through 6 on this dice?
6 out of 6.
6 out of 6, which is 1. So I can have a probability of 0 and I can have a probability of 1. Something either happens or it doesn't. I cannot have a negative probability, and I cannot have a probability of greater than 1. Okay? It's just, there's no way for me to. There's only 6 sides, there's only 6 possible options. I can't have 12 options. Okay? So that is what that means. It has to be greater than or equal to 0 or less than or equal to 1. So we can have a probability of 0.99. But we cannot have a probability of 1.2. We also cannot have a probability of negative 0.1. Okay? We cannot have negative and we cannot have greater than 1. Now, in a sample space, so in any given sample space, the sum of all outcomes for that sample space is 1. It doesn't matter what our sample space is. It could be something as simple as what's the probability of flipping a heads or tails. The max, it could be 1. Has 2 things in the sample space. We can have something with 1,000 things in the sample space, but the max probability is still only 1. Okay? And so we're going to use a coin flip for an example. For a coin flip, we can either have what 2 options? Heads plus the probability of tails. What is the probability of heads? And
Supposed to be 50.
it's 50-50, which means it's 1/2, right? So we have 1/2 plus, what's the probability of tails? 1/2. What is 1/2 plus 1/2? 1. All of our probabilities will add up to 1. That is one of those freak natural occurrences that isn't considered in probability because you would just reflip it. Because that's not a side that you can, that's not going to happen. Okay? So we're going to look at some examples for the rest of class today. Okay? So we're going to look at this first example. It says, what is your favorite color of Skittle? Based on a very large sample, okay, here is the distribution of colors for Skittles that come in the little fun-sized bags. Okay? It tells us that our probability for pulling a green is 0.171. Our probability for pulling a purple is 0.214. Our probability for pulling orange is 0.204. We don't know the probability for red. And our probability for yellow is 0.214. Now, knowing what we know about a sample space, what does all of this need to add up to? 1. Okay? Now, it says explain what the probability of 0.214 for purple means in this setting. What does that mean is happening? No, it doesn't, because that's the same as that. But what does that mean?
That there's a 2 1 4 chance of
How would I write that in a term that makes more sense to most people?
P
How would I write a decimal into something that makes more sense to a lot of people?
fraction.
Percent. Well, how would I write it as a percent?
Oh,
Which would give us 21.4% chance of getting purple. So, not quite a coin flip, but almost. Not a coin flip. A fourth. I mean a fourth. Like a quarter of one. That's what I meant. But now, it says find the probability for red. So if all of these together add up to 1, how would I find what just the red is?
I feel like it's all gonna equal 1.
It all is all going to equal 1. So whenever we were looking at something, find the probability of an event, we can do 1 minus the probability that it is not red. Okay? So in this case, is green red?
Green is not red.
Is purple red?
No.
Orange red? Yellow red? No. So what we can do is we're going to do 1 minus everything that's not red. So 1 minus 0.171 for green, 0.214 for purple, minus 0.204 for orange, and 0.214 for yellow. And what does that give us as the probability for selecting a red? No, all of them add up to 1. That includes red.
Oh.
So every all of them together, all of these, if I was to add them all together, they would equal 1. Okay? So we subtract the ones that aren't red to figure out what red is, because that's the only one left, right? It's like if I gave you this problem here. If I gave you this problem. 7 is equal to 2 plus 3 plus x. How would I solve this? I would subtract, right? It's the same as saying 7 minus 2 minus 3 equals x. So what is 7 minus 2? 5. What is 5 minus 3?
2.
So x is 2.
Oh, yeah.
That's the same thing that's happening here. It's just giving it to us in a probability format. So what is 1 minus 0.171 minus 0.214 minus 0.204 minus 2.214? What is that? It's 0. What?
Oh.
0.197. Okay?
I got you. See the better way to do it. No, that's you add all of the depths.
You could do them all. You could add all those together and then just subtract. You still have to subtract it from 1 though. So you're doing the same thing.
I'll just
Okay? Now, what is the probability that a randomly selected Skittle is green or purple? So we're trying to figure out the probability that it is green or purple. Okay? If I'm only selecting one Skittle, can I grab both a green and a purple?
if
No.
you're getting one.
No. Okay? So that's mutually exclusive, so I can just do the probability of selecting a green plus the probability for selecting a purple. Using that table up there, what is the probability of selecting green? .171 plus what's the probability of selecting purple?
0.2.
So add those together. What do we get?
385.
So that is the probability of selecting green or purple. You just combine it. Okay. What is the probability that a randomly selected Skittle is not yellow? So if we wanted to find that the probability that it is not yellow, I would need to do 1 minus the probability that it is yellow. So it would be 1 minus 0.214, which is what? 786. That is, it was just a very bad 2. All right, now we're going to do one last example together today. Okay. So this one is a question about how prevalent is high cholesterol. Okay. So this has been chosen at American adults at random, and we have 2 events that are defined. Okay. We have event A. Okay. Event A is that a person has high cholesterol, which means they have greater than or equal to 240 milligrams per deciliter of blood. So it's greater than or equal to 240. Okay. Then we have B. Event B is the person has borderline high cholesterol, which is between 200 and 240. Okay. Then it tells us, according to the American Heart Association, 0.16 of American adults have high cholesterol, and 0.29 have borderline high cholesterol. So it says, explain why events A and B are mutually exclusive. Why are those 2 things mutually exclusive? Can they both happen at the same time? Can you have high and borderline at the same time? No. Okay? And so that's what we're going to put. You can't have high cholesterol and borderline high at the same time. You're either one or the other. Then it says, say in plain language, what is the event A or B? Okay? So find the probability of A or B. So what would be A or B in this question? What is A? High cholesterol. What is B? Borderline high cholesterol. So what this is asking is, what is the probability that a person has high or borderline high cholesterol? And so we're going to find that probability of A or B is equal to, we have to do the probability of A plus the probability of B. What is the probability that a person does have high cholesterol? It tells us in the question, what's the probability of A? 0.16. What's the probability of B? Okay, when we're doing these, we will pretty much almost exclusively deal with decimals unless it asks you what it means. Okay, what is 0.16 plus 0.29? It is 0.45. So that is the probability that it's high or borderline. Then it says, let C be the event that a person has normal cholesterol. Okay, so if it's normal, that means it's not what? It's not high, or it's not borderline. So to do this, we're going to do the probability of C is equal to 1 minus, what was the probability that it's high or borderline? 0.45. So what is 1 minus 0.45? So about 55% of adult Americans have normal cholesterol. That's what that means. Okay. So we're going to look at number 9. Okay. Can 0.45 be a probability? Yeah. Can 1/6 be a probability? Can negative 0.34? Can 8/3 be a probability? No. Why can 8/3 not be a probability? Because it's greater than 1, right? It's bigger than 1. Because 8 divided by 3 would be 2 point something, 2.5, something around in there. What about negative 1/2? Is that a probability? Can 0 be a probability? Mm-hmm. What about 1? Can 1 be a probability? Can 30% be a probability? Yeah. Because what is 30% the same as? 0.3. So that works. And we will pick up there tomorrow.